Good afternoon, students. Today we will try to see the pool boiling curve. In the earlier lectures, we have seen the different types of boiling. Today we will try to see the pool boiling curve and the significance of the salient points in the pool boiling regime curve here. So in the pool boiling, the fluid is not forced to flow by any external agency. Any external agency, any motion of the fluid is due to the natural convection currents and motion of the bubbles under the influence of the buoyancy effect here. So the different regions in the pool boiling are the natural convection boiling, nucleate boiling, transition boiling, and film boiling here. So this is a typical curve obtained for a platinum wire submerged in water liquid bath, and it is supplied periodically and is supplied by electrical current. By varying the excess temperature or by varying the input current to the platinum electrical wire, we get a typical pool boiling curve as shown in the figure here. So this plot is drawn between the heat flux versus the excess temperature here. So in the further slides, we will try to see in this given video, we will try to see the significance of the various regimes in the pool boiling here. In this given video, we will try to see the natural convection boiling and nucleate boiling in the first half of the pool boiling curve here. This in the first of this full boiling curve, we could see these two distinct boiling things are observed. One is the natural convection boiling, another one is the nucleate boiling here. So in this region is almost called as the free convection zone. The excess temperature, that is a delta T, T S minus T sat, is very small and is almost equal to 5 degrees Celsius. So here the liquid near the surface is superheated slightly, and the convection currents circulate the liquid and evaporation takes place at the liquid surface here. So this liquid is in this region is slightly superheated, and we call it as metastable state here. So heat transfer predominantly in this regime, it takes place by the natural convection effect here, and the delta T is equal to 5 degrees Celsius in this natural convection boiling. Further, as delta T is increased, beyond 5 degrees Celsius, we get the nucleate boiling regime here. Here we could see three different points as highlighted in the curve, point A, B, and C here. So you could see this as heat delta T is increased further. You could see this, there is a more tendency of formation of bubbles, which readily forms and gets collapsed in the liquid itself here. So region A to B is the isolated bubbles region, and region B to C is the continuous columns of vapors formed in the liquid here. So point A is referred to as the onset of the nucleate boiling here. So the real boiling starts at point A, that's referred to as onset of nucleate boiling here. In region A to B, the stirring and agitation caused by the entrainment of the liquid to the heater surface is primarily responsible for the increased heat transfer coefficient here. So as you progress from delta T 5 to 10, you could see that heat flux is also increasing here. In region A to B, the large heat fluxes are obtainable in this region and are caused by the combined effect of the liquid entrainment and the evaporation here. So after point B, the heat flux increases uh, at a lower rate with increasing delta T and reaches a maximum point C here. The heat flux at this point is called as the critical heat flux or maximum heat flux, and is of very much primary engineering importance here. So this is very much important for as delta T increases is increased beyond 5 degrees Celsius to 10 degrees Celsius. You could see that bubble is formed, which readily forms and gets collapsed in the liquid here. When the delta T is increased beyond 10 degrees Celsius, we reach a point called as the maximum heat flux. It's a critical heat flux, is very important. Further things we will see in the next video here. Thank you.